Okay, we're on the 14th of March, fastly approaching spring break. Fastly approaching the end of the semester is what I almost feel like because I'm in such a whirlwind. I got all the page proofs from my book yesterday. They want me to have them reviewed in 1 week's time. That's 400 pages plus of writing. Check all the equations. So I feel like the blur continues, at least from my point of view. If you're in senior design, you've got a hard day tomorrow morning, but then you can relax after that. So, or not relax. For me, there's no relaxing, and I'm going to give you some hints on the project. One of the first things I want to do, though, is get off into a really hands-on topic that has been in the lab, I think, for a bit of time now. I've got my dongle to plug in for running ADS here. So let's talk about one of the really hardware-ish oriented comm theory topics. Probably one of the most hardware oriented of anything that we do the entire semester is right here. And then we'll come back and talk about the project, and I'll take questions like from Kelsey, who I know has a project question, and Rob maybe has another project question, I don't know, from last time. Rob was so brave that he came in before the final, or between the exam, not to talk about the exam, but to just talk about the project.
It's a bold move, Rob.
So, got to give him some credit for that.
Does bold mean stupid in this context?
Well, it depends. It depends on what your grade is on the exam, I guess.
That's a scary idea.
You know, you do what you think you got to do, and that's what you thought you had to do. That's a good move, actually.
Are we not doing section 3.1.4?
Correct, because that is on vestigial sideband, and that is NTSC was the prime example of that. What's that?
It's pi day today.
Okay.
That'd be kind of funny. Oh.
Okay, so frequency translation and mixing. This is something that if you're even remotely connected with communications in your future, you will be dealing with this subject. And in the block diagram, it looks fairly insignificant, but I do have a typo in here. This is supposed to say omega 2. But the whole idea of frequency translating and mixing is being able to take a signal and move it from one location to another. So the way this picture is showing it is I'm moving it from F1 to F2. And the main elements for doing that are a multiplier, which is called a mixer, and I'm going to explain that in a second, why it's called a mixer. And if you're into cooking, it's not that kind of a mixer, like the one you have in the kitchen that you mix foods up in, but it is related to that, though, in an abstract way. And then a bandpass filter that's centered on F2. So what are the requirements to do a frequency translation in hardware is to have a local oscillator, as it's called, or LO in the terminology of RF systems engineering, a local oscillator that sits either above or below the frequency F1 by F2. And so that's what the math down here is saying. It's basically saying set the local oscillator either at omega 1 plus omega 2 or omega 1 minus omega 2. And it's relying on the trig identity that we've seen before. When you take cosine times cosine, you get cosine of the sum and cosine of the difference. And that's just the modulation theorem, right, in action. So whatever is present at the input, multiply by cosine omega LOT, and throw the 2 on here just for the mathematical beauty of having the 1/2 from the trig identity cancel that out. It's not strictly a requirement in hardware, but in the math it makes it look prettier. So what we get out of the mixer then, at the multiplier, is the desired signal is this guy right in here, and then this is the other product term from the trig identity. That's the unwanted term. Oops. But the unwanted term is disposed of by the bandpass filter. So the bandpass filter can throw that term away. is what we count on it doing. But there is a recognition of the fact that that term could go somewhere. In other words, once those two terms are generated inside your analog hardware, there's the potentiality for even an unwanted term to get out on the loose, so to speak, and it cause interference. So you do end up having to worry about things like that. Where they go to, how you terminate, how you shield and isolate the unwanted term. The bandwidth of the bandpass filter has to be at least twice the bandwidth, or the bandwidth of the signal coming in, and if it's double sidebands, it's going to be 2W. If it was single sideband, it'd be W. If it's some other modulation scheme, it's whatever the RF bandwidth is of the signal that you're translating. Now, one of the downsides of this simple little idea of frequency translating and mixing is that there's another signal, there's always another signal that can come through the same block diagram. So there's another signal that could sit out here at a different frequency. Actually, I should draw it as a different shape. It's called the image frequency. Draw a very good E there. There's always another frequency, F image, that can also get translated down to F2 or get converted to F2 by that multiplication. And mathematically, that's just a signal that sits at omega 1 plus and minus 2 times omega 2. And then I'm going to make that clear in a picture that's coming up with this example. It's basically if the local oscillator can sit omega 2 above omega 1, then I could sit another signal, another omega 2 above that, and it would down convert, or it would get converted to omega 2 as well. And like I said, you'll see graphically, this is kind of like when you're figuring out aliasing. Remember in sampling theory, this is a little bit along those same lines. There's alternate frequencies that convert in to the same place.
So is that K of T then? Is that the F image type signal that's being...
K of T would be like the modulation. This could represent the modulation.
Like somebody else using the same channel?
Yeah. Yep. Well, using a different channel, but would get converted.
Using it would be like a different channel, like, but at twice the frequency that. So
Well,
that channel is.
at the frequency omega 2 above the local oscillator frequency. So it's at omega 1 plus and minus 2 omega 2.
But does that K of T, that's what causes the actual image frequency to occur?
Now it's really just the frequency itself. This is the key. The key idea is that it's pick a different color. Omega image is at omega 1 plus and minus 2 omega 2. Okay, actually, see, I got ahead of myself. It's right down here. And then the local oscillator is always omega 1 plus and minus omega 2, so the plus and minus signs track. The image is plus 2 omega 2 if it's the plus omega 2 local oscillator, and it's the minus if it's the minus. So a practical example, sort of an old-fashioned example, is AM broadcast superheterodyne receiver. We haven't really got into this aspect of hardware at all, but when we were talking about double sideband and AM, we just said the signal comes into the coherent demodulator, and we take it down to baseband, apply the low-pass filter, and our message is back. But in practical terms, you don't build a front end that directly converts to baseband very often. Generally, you have a frequency converter that converts it to a common frequency. In SATCOM, it's generally 70 megahertz is the intermediate frequency. In FM radio, it used to be 10.7 megahertz, and this is one of the chassis from the lab experiment, which we'll be looking at the block diagram for this shortly. And in AM broadcast, in the olden days, the IF frequency was always 455 kilohertz. It depends on applications, and there's reasons to do one thing versus another, and this receiver happens to be what's called dual conversion, and we're going to look at the dual conversion idea here as well. But this is a simple old-fashioned AM radio. It gets the point across, and the superheterodyne concept, I don't know if you remember from the history at the beginning of the very beginning of the course and in the book, I think it was Armstrong also developed the superheterodyne concept back in the early part of last century. So it's been around for a long time. It's a fundamental radio principle, though. It's not modern high-tech stuff, but it's fundamental bread and butter stuff that you need to do. Virtually every radio receiver and transmitters typically have these converters in them. And you have them at home as well when you have a set-top box on your TV. If you don't have a TV that has the ability to convert everything from the standard cable network that we have, Comcast rents you a box, right, or signs one out to you, just because every cable company can allocate the way it uses different frequency spectra differently, and when you buy a TV set, it might not conform exactly to what that cable company is doing. So the cable company then says, I'll build this custom box that will translate signals from the way they put them on the cable to a common set of frequencies that can be used into your TV. And nowadays, rather than coming in on a particular channel, I think it comes in, at least on mine, it comes in on an HDMI port, right? Does anybody know how their TV is set up at home? Am I right, though? Pretty sure ours is HDMI, because we have a HD TV, and it has like 3 HDMI ports on it, and one of them connects to this cable box. And that's what the Comcast remote control is controlling, and that's basically a frequency translator box with some other fancy stuff inside of it. They've gotten a lot more sophisticated. So AM broadcast goes from 540 to 1600 kilohertz, which these days with multi-gigahertz clocks in PCs, you'd think you could almost sing at that frequency. You can't, though, right? Because that's above human hearing. But that was considered radio frequencies that were hard to build circuits for a long, long time ago. So some other facts about it is it's flat from 100 hertz to 5 kilohertz, which is why the audio quality is rather poor. It's kind of like the speech vectors for this project. A little bit higher fidelity, but not much. They're assigned to carriers that are at 10 kilohertz spacings for AM radio. So if you build a superheterodyne receiver, what you're doing is you're going to bring your signal in from the antenna, generally through a tunable front end that can add some selectivity, and I'll explain that in a in a graphic on the next page. Then you have a local oscillator, and notice it's set to, this is basically the omega 1 plus and minus omega 2 idea, because the IF frequency in this case, FIF, is at 455 kilohertz, and that is like F2 in the earlier notes. So we're going to convert everything to a common frequency. What you can do at a common frequency is you can build a highly selective bandpass filter to pass just the signal right at 455 plus and minus 5 kilohertz, so that anything else adjacent to it will not leak through. You can put high gain on it because you're at a narrow band of frequencies. You don't have to worry about it getting overloaded with other interference. And then you can put your envelope detector and audio amplifier if it's an AM radio. And again, this is pretty old-fashioned because they've been around a long time, but it still has the basic foundational concepts. So how can you set your local oscillator? Well, you can do one of two choices. You can do the low side tuning, which is the omega 1 minus omega 2. So there you'd want to set your local oscillator to start at 455, subtracted from the lowest frequency you need to receive at, up to 1600 minus the 455. So the LO in that case tunes from 85 to 1145. Pretty simple. Unfortunately, the better design, or Not really unfortunately, but the fact of the matter is the better design is to go with the high side tuning, as it's called. So you'd set your local oscillator to tune from 540 plus 455 up to 1600 plus 455. Now, why am I doing this adding or subtracting? Well, the local oscillator is getting multiplied against the received signal, and we're looking for the difference to land at 455, right? So by setting the oscillator above by 455, then when we receive a signal at 540, the difference comes out at 455 all the time. The sum in this case is advantageous because if you look at the ratio that the oscillator has to tune over, this ratio is the smallest when we put the frequency up higher. So that in the olden days, that made it easier to build the oscillator. Today it's still a factor in building a voltage controlled oscillator even. But if it was all done in digital signal processing, it really wouldn't matter that much. If it was done in analog, that's where it matters. And converters are generally done in analog when they're at microwave frequencies. Yeah?
Why is it better to have the high side in comparison to the low side?
Well,
So it's better design.
just because of this ratio, FLO max to FLO min is smaller, so the oscillator doesn't have to tune percentage-wise over the same range of frequencies. It still tunes over the same kilohertz region, delta kilohertz, but the ratio of the maximum to the minimum is smaller. And when you build RF circuits, it's a matter of how easily you can tune them over a band of frequencies. And if you can keep that ratio smaller for the tuning elements, then the inductor and capacitor values are more readily achievable. So an example we're going to take in this picture is, suppose you want to get a station at 540 kilohertz or 560 kilohertz. So this is what we want to receive. So this will be the desired, oops, what am I doing here? That's the desired signal. So I'm going to choose high side tuning. So I set the local oscillator to 455 plus 560. So it's at 1015 kilohertz. So if you go down here, you can see that the desired signal, this is the input and this is the LO piece of the chart. Desired signal is sitting there at 560. I put the local oscillator right in here at 1015, and notice how it's FIF above 560, so the difference is assured to put a different signal down here, right down here, centered at 455, because 1015 minus 560 is 455. See, this doesn't involve any calculus or anything. It's just simple algebra. Well, it's trig, identity, that got you the formula, but it's just algebra at this point. See how nice that is? But now you can also see from this graphic how that image can get in. The image sits at 455 above the local oscillator. See how that's shown in the picture? This total span in here is 2FIF, and that's the requirements for the image. The image is sitting at 455 above the local oscillator, and it also produces a difference when multiplied by that local oscillator at 455. So that's why in this very last figure I'm showing that it will also come in to the receiver. And 1470 kilohertz is another AM radio station. So what you were saying a little while ago, Rob, two signals can actually get down converted and land on top of each other, which is not good. So what's the remedy for that? Exactly. So that dashed line over the desired signal there is the RF tunable filter that was in the block diagram. That dashed line represents, this guy right out here. And the fact that it's arrowed over to the local oscillator says that it does have to have some tuning. It does have to have some tunability, because it's responsible for rejecting the image. Does that make sense?
So
This is a real simple concept when you get right down, but it's extremely important. And I think one of the things you probably learned being in school all these years is that what do you think is going to be the most important on a day-to-day engineering lifestyle of getting your work done? The most intricate, involved concepts or the fundamental concepts? And the fundamental concepts are what get the job done most of the time. You only need the really detailed, hairy stuff every now and then. But if you don't have the concepts down, you can't design. So, and this is one of these things that is just foundational. It's bread and butter type concepts. So much so that an RF systems engineer, which might have be a comms type person, or vice versa, a comms person might minor in RF side, they would call this a frequency plan and look at the potentialities for how they're going to make sure that certain things do or don't happen. I mean, you do receive what you want to get, you don't receive what you don't want to get, and you don't generate other spurious signals, like out of that mixer, the desired signal gets shifted up to 1575. If that signal were to leak somewhere else within my analog circuitry, would that cause me harm? There could be another converter or another mixer running around somewhere, and that signal could cause some headaches. So a good RF systems engineer would use some tool, maybe a spreadsheet or something, and work out different frequency plan ideas to make sure that it's sound and you can protect things from happening that you don't want to have happen. Now, one of the problems with the front end having to tune is that this effectively has to tune with the local oscillator. So as I want to tune up, so I want to move the local oscillator up higher in frequency to actually receive 1470. I need to make sure that that dashed line, red line, actually moves up as I move the local oscillator, so I'm capturing the signal that I want to get. Now, just as a simple little check here, if I'm going to tune my local oscillator on the high side to receive at 1470, what do I have to do? I have to add 455 onto 1470, right? So now my local oscillator would sit somewhere up in here. So that's 455 plus 1470, and that's 19 something or another. You got to think about the math. 12. Is that 1925? Is that what it is? Oh, is everybody following? That'd be the high side tuning relative to this guy. So that will let me receive the 1470, but now there's going to be what? Where's the image for that 1975 going to occur? It's going to be up here. So that's another 455 onto the 1925. So that's 2380, is that right? 2380 kilohertz. So what's up there? Well, we'd have to go to the FCC chart and see what could be powerful enough to possibly make it into our receiver. Because that dashed line that represents that front end filter, is that going to be a brick wall filter in reality? No. So it's going to have skirts that are down so many dB out in that vicinity, and hopefully by knocking the signal down maybe 10, 20, 30 dB, hopefully more than that, it doesn't cause a problem for us. But
is that 1575 signal? Is that because from the image, or is that rather from?
That's because you get yeah, it's the sum.
Okay.
That's just to make you cognizant of the fact that there's this other signal that's now inside your hardware, and the filter is supposed to absorb that, but it's still in there. And analog circuit design is not something you master quickly when you're in school. I mean, there's a lot of nuances to it. When there's weak signals around and strong signals around, weak signals can get corrupted by strong signals, and that signal could actually turn up somewhere else in the system. And it might be harmful. So you might have to put in better shielding, better grounding, or you might come up with a different frequency plan because that 1575 might just be, you can't tolerate that. So you've got to set up a different frequency plan. which means you maybe don't use 455, or maybe you use a dual conversion or something. This is why it's amazing with all the electronics we have, with all the oscillators, and we have radios that can still work, because you think about harmonics and spurious signals, you know, what keeps everything from not interfering with everything else? There's a lot of junk out there. And those of you in the comm lab, have you been noticing that you see things on the spectrum analyzer that are like, where does this come from? I hold this wire, I'm putting my finger on the end of the wire, and the spectrum analyzer picks up all these other signals. Some of it comes from the scan frequency harmonics off the display. There's garbage floating around everywhere. And with a spectrum analyzer, you see it, and it's like, this is really a dirty environment that we're in, right? I mean, that's one of the things you're supposed to be appreciating in the lab. And I originally thought, this lab is not too good because you see all this junk, but then it's like, well, this is the way it really is. It's not that perfect. You just deal with it, and there's no such thing as, you know, perfection when it comes to radio signals. So does this make sense, the idea of the conversion?
So does that still occur even if you were completely demodulating the signals and putting it to intermediate frequency?
Well, like I was saying earlier, generally if you're going to receive at multiple frequencies, you want to have some sort of front end that you can convert it to a common frequency, and then put all your expensive processing and filtering in this chain here that's fixed. And this would maybe be, this would be a synthesized oscillator. It would be programmable by computer.
Okay, so you're essentially you're doing 2 bandpass filters on it, one to filter out everything.
The images.
all the
So,
images.
yeah, a quiz question could be, what's the purpose of the the RF filter on the front end? That's to reject images, right? And then the IF filter is to give your selectivity to get just the channel of interest, because here's the other thing that will happen is if there's another station that was parked,
Right here.
yeah, suppose there's another station right in here, or there's another station right in there. What's going to happen when we do our frequency translation and mixing? First of all, let's think about what happens here, because this is another thing to think about for those of you in the comm lab. If I set my local oscillator on the high side at 1015, which of these is the order of the signals going to come out over on my mixer output? This one right here is closer to the 1015, so where does it come out down below here?
It'd be closer to
It comes out at a lower frequency, right?
First.
So it comes out down in here, and the other one comes out in here. So things flip around. And in the radio experiments you do with these modules, you get to look at that in the spectrum analyzer and tune it and watch it, see it flipped over like that. But if the receiver, now the demodulator, doesn't have a narrow enough IF filter on its front end, these two signals that I've shown either side of it will get in and cause problems, especially with an envelope detector. I actually put a pretty neat example of that in my book because it was just something that I thought was kind of cool to analyze. It's pretty simple to analyze, but it's actually more complicated than you think, because the envelope detector is a nonlinear processing element, and nonlinear processing elements tend to do things that aren't really friendly. I mean, they do ugly things. They do what they want them to do, but they also produce other side effects.
That's a quick question. So, if you were to do that right signal, which is like the one with the little spike,
Yeah.
wouldn't it? Why is it on the left? Wouldn't it be on the right, since you have 1015 minus a higher frequency than 160, which would result in a higher frequency?
Well, I'm drawing the line down here, and I'm saying that when I do the difference, that's closer. The difference is smaller, so it's going to sit off to the left because it's at a lower frequency.
Oh, okay. I see now.
Does everybody see that? I'll have to fit that into a quiz somehow or another. Have you draw the spectra like I just drew here for more than one signal. What you're doing in the project is coherent demodulation, so you're just taking the whole spectrum here and you're just, well, I guess from your orientation it's sitting up high and you're just sliding it over to baseband. and you're getting back the signal that you want.
You don't need to do the band pass in front of it.
Well, you do need to do the band pass, though, because of the fact that you need to do it,
To get the one signal out the
yeah, like I said last time. Otherwise, you get additional interference, and it has to do with some folding action that occurs in the downsampling, too. Okay, here's what's in this chassis, which I'll pass around right now. This has got active mixers in it, and it's got the dual conversion receiver. It's exactly this idea right here is what's implemented. This is what we call the wideband. No, this is the narrowband receiver.
That's the narrowband?
Yeah. You're working on lap 4?
Yeah.
Okay, this is the narrowband one. And so what it does is it receives weather channel. It's set up to tune over a range of frequencies with the synthesized source in the lab, but it was designed, say, to receive 162.475 megahertz. So the first thing we do is convert to 10.7 megahertz. And that requires, what kind of tuning am I using if I set my LO at that frequency?
upper.
So it's the high side tuning. So that frequency must be 10.7 above 162.475. Does that sound right? So the difference comes out at 10.7. And then the sum frequency is at 335 megahertz. So why would I want to do that? Why would I want to pick a high IF frequency? Let's see if we can think of an example why that would be important.
Talking about the 10.7 one?
Yeah, why would I pick, if the signal is narrow band, and this happens to be a very narrow band signal, the weather channel, weather radio, does anybody ever listen to weather radio? You know a weather radio?
They have the emergency.
No?
They have the emergency radios or whatever that pick it up.
Another radio that picks it up is the FRS radio that I have. I mean, Family Radio Service. Do you ever use those? Those little palm-sized radios you can use like when you're carpooling or caravanning somewhere. Or my family, we bought them for when we went to Disney World. We could split up and we could talk to each other in a park. People use them for hunting, other things. Some of them now have GPSs built into them, so the GPS coordinates go through a data stream, and then the other radio picks it up, and you can see where your cohorts are hanging out. It takes the place of a cell phone because out in the wilderness you don't have access to a cell tower. At any rate, it's a narrowband signal. It's more like the bandwidth of an AM radio signal, but it's at a higher frequency. So we really want a narrowband processing for that narrowband signal, but one of the advantages of going to this higher frequency IF is that if I do my frequency plan and draw a little picture out as to what I'm trying to do, I'm going to down convert to 10.7, and I'm wanting to receive 163 or 162, and I put my local oscillator up at 173. So there's my desired right there. My image frequency is going to be up over here at 10.7 above that, right? I won't fill that in. I'm tired of trying to calculate the simple math out, but this is F image. So what I managed to do, even though it's a very narrow band signal, what is it? You guys have to do this when you do the lab, so you have to think about it a little bit. But by having the IF frequency higher, because it's always twice the IF frequency is the separation between the image and the desired, I can move it further away, and then it's easier to get rid of it. Does that make sense? If the image is further away from the desired, then it's easier to put a filter over the desired and have the skirts of that filter drop off and not let the image leak in. So that's the plus about having a higher frequency IF. The minus, though, is that you want to have a narrowband filter, and to build a narrowband filter at a higher frequency is harder from the RF circuit design standpoint, because an RF filter, the bandwidth of the filter is a function of its center frequency. Maybe it's a 5% of the center frequency is a good rule of thumb, or up to 10%. But you can't get it down much less than that without having serious manufacturing issues. So it's kind of like in a good engineering problem, you try to do something to help you out in one area, get the image further away so you can eliminate it, but now you have a harder time getting the narrow selectivity that you're looking for. So the solution is to go through a second stage of conversion. Now we've got the signal at 10.7 megahertz. We've been able to get rid of the image effectively by having the high IF frequency. Now we come along and convert it a second time down to a narrower IF. So we have a fixed oscillator, and on that board I'm passing around there's a crystal oscillator in there, and if you read the end of that crystal it'll say 11.155. I went to a company, international crystal company, and I said, I want this frequency. And they readily made it for me because it's kind of a common frequency, but that was a custom order to get. It's not like a clock oscillator in a microcontroller. This is in RF stuff. You get crystals made for very precise requirements. So this one is at 11.155. And it sits at 455 above 10.7, and now I'm again susceptible to the image frequency, but because I've already had this first stage of IF conversion take place, I'm less likely to have an image come in because I've got a couple of filters in front of it to protect the system from images. But now I can design this narrower or lower frequency IF to have a narrower bandwidth. And I think I talk about that in the bullet points. This is an FM modulation scheme, but it's okay. Question?
It's kind of a general question, but I think it has to do with this. Does the amount of data you can transmit over a channel depend on the bandwidth, no matter where the bandwidth is? Like, it makes intuitive sense from like with the audio data we've dealt with. Like, it doesn't matter if you're at 50 megahertz or 200 megahertz. It's still 20 kilohertz of bandwidth.
Correct.
To shift up or down.
But the FCC recognizes the fact when they make allocations that as you go up higher in frequency, the fractional bandwidth, again, like 5% of the center frequency, is going to be a bigger number of hertz. So you tend to get an assignment of a wider frequency band as you go up higher in frequency, just because it's a fraction, it's based off the fractional bandwidth idea. And that's kind of a limitation imposed by our circuit designs too, from forever, basically, from the beginning of radio. So the FMD mod part we'll talk about coming up next. That's the next topic after this. So if I was to give you at some point a block diagram for a dual conversion or single conversion, and you had to fill in some details like the parameters, what bandwidth here, local oscillators and things, think you can do it? I mean, after you look at some problems that are in the example problems in the book, or I mean, it's like a back of the envelope calculator. It doesn't revolve around Fourier transforms per se. It just is adding and subtracting. Hypothesizing I can put a filter here, and then I can do this, and I can protect this from the image and make this bandwidth narrow enough to only pass that signal through the IF to give the selectivity so I don't leak other signals through. You have a question?
Yeah. What's the I see what the 10.7 megahertz and the 455 kilohertz is, but what's the 335.65 megahertz?
That's the sum frequency. This is the sum right in here. So that's what's present in here. So there's something at 335. So if you didn't do a good job of filtering that, and that signal was to radiate out of your box, and there was another receiver nearby, it could possibly get into that. But, in the world of RF stuff, you just got to be careful. You got weak signals, and you got to make sure, which is why computers and other electronics can be an issue. That's why they have to be shielded. That's why they have to go through FCC requirements testing, so that somebody doesn't introduce a product on the market that every time it gets close to a sensitive receiver like a GPS or something, it causes problems. Or I think that's the theory, the reason why the aircraft industry makes you turn off all your devices when you're taking off, because they're using instrument landing systems and they don't want to have those any harmonics or mixing products get in and desensitize the ability to get accurate position information. Because I think the modern airplane can fly itself down to a landing pretty much if it's got the right GPS signals to work with. I mean, it doesn't maybe do that very often, but the pilots can let it do that.
So the reason that you use high side
tuning here
is so that your image frequency is at a higher frequency than.
Yeah, in this case, it just depends on the frequency plan. Again, if you thought there was a potential threat more from the high side or the low side, then you would pick where the threats might lie.
Okay.
I'm saying threat in a friendly way. I mean, threat is just another application that you know that there's a strong signal.
Another station if there was one on the high side and one on the low.
But again, just like in the previous receiver, if you do high side tuning, the fractional or ratio of min to max is smaller, and it's easier to build that oscillator.
So the ratio is still.
But in the ComLab experiments, you're encouraged to experiment with both high side and low side tuning, and you found it works on both sides, right?
Yeah.
Was it vivid? I mean, the intention of the lab is to make this all crystal clear by actually seeing it work, and that was the point of building those boxes. So. I was supposed to have gone through this before you did the lab, but
that's okay.
it's probably the most fun lab because it's pretty much all built, but you get to drive it and you get to probe it. So, and Les has done an excellent job of taking my original design, which was on a proto board, an RF proto board, and putting it into those chassis with the PCBs.
Dr. Wickett, I have a question. So for the second IF filter, it can have a much narrower band, because when you're centered around a smaller frequency, you can, having a narrow band doesn't affect. Like if you were centered around a higher frequency, having a narrow band would be problematic because you could pick up more like 100 kilohertz rather than just like kilohertz.
It has to do with
it's
the fraction. It's the circuit limitations. You have to be. The bandwidth is controlled as a fraction of the center frequency, say 5 to 10%. If you try to get too wide, you have a problem. If you try to get too narrow, then you require inductors that have really high Q and capacitors that have really high Q effectively, and you just can't get your filter to work. Or if you can get it to work, it has a lot of insertion loss, and then that's not good either.
So because it's on that higher frequency, it's harder to get your
narrower bandwidth. You can't get. It's easier because it's like a 10% of the center frequency. So.
Okay.
So if we wanted to have a bandwidth of 10 kilohertz, 10 kilohertz divided by 455 kilohertz, that's what is that? 5 into 20%, is that right? Or 2%? My brain's not thinking right now. What's 10? Yeah, 10 kilohertz is what you need here. 10 kilohertz divided by 455, or 10 divided by 455 times 100. So it's 20. Yeah, 1/5, 20%. So it's a 20% bandwidth. That's quite doable actually. But if you'd had to take 10.7 divided into 10 kilohertz, what fraction is that? That's less than 1%, isn't it? That's like, can't do that. Sorry. Now for FM broadcast, you do it at 10.7, but you need a 200 kilohertz wide filter, so it's a lot wider, and then that's doable in the technology. This is not an R circuits design class, but I think a radio engineer should know a little bit about some of the limitations. Okay, mixers is the next topic that's in here. Just a little bit about the mixing idea. A multiplier is what the symbol is. So we're used to the multiplier symbol as just being one signal times the other, x1, x2, and then what comes out here is the product, x1 times x2. But an ideal multiplier is not possible in analog electronics. It's going to have some limitation. And the term mixing comes about, I think, from the early days of saying we don't even know how to build a piece of electronics that's actually going to multiply signals in the traditional sense. In the early days, the idea was that you could pass the sum of two signals through a nonlinearity. So for example, if you put two signals inside a device that has a squaring characteristic, which is what I've got shown right here, what happens when you factor out that squaring? You get three terms, right? You get the signal squared, second signal squared, but then that's what you're after. But that's just one of many terms that comes out. It's like you get all this other stuff, but you do get one term that you want, the product. And that's just assuming the device has a pure square law characteristic, but any nonlinear device is going to have other terms. So mixing produces a lot of other terms in general. So a simplified schematic of that, a mixer concept, is where two signals can be brought in, they go through some nonlinearity, and then you have the output. And then a schematic that I pulled off the internet a few years back is a metal semiconductor FET, or MESFET, microwave mixer. And this is a dual gate FET. So both signals are being summed in through their own inputs, gates. And then rather than making this act as a linear device, we're purposefully biasing it so that it acts as a nonlinear device. So we get the square law effect out of it. And then that produces the desired terms. A more controllable and favorable type of mixer is what you use in the comm lab, the double balance mixer, which has a diode ring and some transformers in it. So this is the form of a double balance mixer, and there were active versions of the double balance mixer on the radio I passed around. This is a little tiny one from Mini Circuits. This is an active double balance mixer from Motorola many years ago. This has 3 ports on it, so it looks like a mixer should. It has 2 inputs and an output. And this is the one that, the DBM, as they're called, is what you use in the comm lab. And if I can get ADS to launch here, I'll just show you quickly a little bit about what can happen. So we're going to go into these schematics or projects are in the website for EC4670, so even if you're not in the lab and you wanted to play with them, they're available there. So first off, I'll just show you a really quick example of it. This is just looking at creating a modulator with a 1 megahertz carrier and a 50 kilohertz single tone message. And this is the model for my mixer. It's a sub-circuit, so if I push into it, I can see that it's this setup of the 4 diodes set up in a ring, and then it's got these center tap transformers. So you've got a local oscillator coming out of the center tap here is called the IF, and then you have the RF that comes in here. So generally you drive the LO port hard so that it gets the diodes, alternate pairs of the diodes turning on and off, so it's acting like a switch, flipping the polarity back and forth of the current flow. And then the RF is the weaker signal. It comes along coupled through the transformer, and it's getting essentially flipped back and forth in polarity by the switching action of the local oscillator. And then you tap off at the center point here in a balanced to unbalanced configuration, and that's your product signal. And this is useful for phase lock loops. The little RF board that I'm passing around, that was used as a phase detector in a phase lock loop experiment, of which you do in the comm lab later on this semester. So if I run this, and I'm not actually going to run it, I'm just going to bring up the results of running it as this dBm results over here. I'm not driving it particularly hard, but I'm driving it with a 1 megahertz signal and a 50 kilohertz signal. So these are the two sidebands. This is like creating a double sideband modulator. And that's what we want, those two sidebands. These are the harmonics that are produced as extra products coming out of the so-called multiplier output. And then these are the first odd harmonics of the local oscillator at 1 megahertz. And then other things. So in general, you see a lot of garbage coming out of here, a lot of things that aren't directly the products. But again, if you're in the comm lab, you got used to this and you're kind of understand that these things do exist. Just it's the nature of the circuit. You get extra harmonics, all for nothing. I'm saying that facetiously because you really don't want them, but you do get them.
Kind of makes this output signal kind of.
Yeah, it kind of makes things look kind of bad. But if you build up a little bit more complicated circuit, double sideband transmitter receiver, this is a coherent modulator and demodulator setup. So I come in with a 1 megahertz signal. I go through a power splitter so that I can split a copy of the carrier up to the first mixer right here. And this power splitter is just a simple resistor network which stays matched to 50 ohms. And what I mean by matched to 50 ohms, if I terminate this port with 50, this one with 50, and I look into this port over here, I will see 50 ohms. So if I look in any direction with the other ports properly terminated, it always looks like 50. It's called it's a resistive power splitter. It has loss, but it's simple to make. So when I worked in industry, we used these frequently. So I split off so I get a copy just to demodulate in this other multiplier over here. And if I run that circuit, which I'm not going to run, I'm just going to look at the results. It does a pretty good job if I keep the levels adjusted right. There was a signal originally that we looked at before that had the sidebands, only this time at 10 kilohertz, about 1 megahertz. I coherently demodulate, and right down in here is exactly, get the marker to sit on that. It's not sitting.
You gotta go over the marker and drag it, I think.
Yeah, that's right. Got to go to the marker there.
And move down.
So there that is, and it's getting a harmonic component out that's about 40 dB below it. So it's pretty good, actually. It's pretty clean. And then this is the sum frequency, and then that harmonic is kind of unwanted. So it's doing a fairly decent job, actually. You just got to look at things carefully, and that's where the spectrum analyzer comes in so handy, because if you look in the time domain, I see that's what the waveform should look like coming out of the demodulator. It should look like it contains the double frequency term, which is that filled in red stuff, and then the sinusoid is the baseband term. If I filter out the double frequency term, I see just the pure sinusoid, right? Because we went through that already in class. So that's kind of reassuring. It's kind of what I like about ADS is I can actually put up a circuit model, because if you're a circuits designer and you're just working with math on the page, you tend to say, this is too ideal. I don't trust anything I can do with purely math on the page. I need to simulate something and see if I can make a circuit create a usable signal. That was me when I was first in industry. I think I told you I worked at the bench all the time, and I had to make stuff work, because that's how you made money. You sold stuff to the customer. Math on the page, as I call it, wasn't going to make you any money. And any place I work today, it's the same story. The analysis helps you get there, but they're selling hardware, so you got to be able to do that. I could show you other things, but I want to move on and talk some about the project before we get out of here. I've got a single diode mixer. You can look at that in the notes, and it's just pretty in the rough. It's just summing two signals, and it actually works too. We're going to start with take up angle modulation, which will give us phase modulation and frequency modulation. We'll get into those topics next week. When you first look at these definitions of angle modulation, you'll say, this looks a little bit familiar from 2610 when you looked briefly in one of the chapters at instantaneous frequency. If you can remember back to those days. So this is going to be the more formal discussion. We'll get into Bessel functions so we can study sidebands of FM signals, and you'll find that that's one of the most mathematical things we'll look at is special functions. Let's go back to the project though and see if I can answer some questions. And we'll come back to FM if I run out of time, but I'm suspicious that maybe I'm going to be answering some questions for a while. I'd like to volunteer certain information that it's on my mind as the next phase of what you were going to have to do at the end of the project, but I'll take questions first if there are any. Anybody have any questions? What was your question?
What exactly my question is, so I'll let you talk.
Okay. Well, I'll wait. I'll go last.
I had a question, I guess, concerning when I was able to modulate it and demodulate it, but looking at I ran a noise signal through it.
Okay, which is good for
so
testing.
It was perfectly flat coming in, but on the output it seemed like the low frequencies were increased about, what was it, about 10 dB. And then as it got to higher frequencies around 3K, it decreased and went down.
Okay. So maybe we need to look at you need to talk about your topology of what you were doing. So what you do with a coherent demodulator when you're still sampling at Fs over 2, you're coming in and you're doing your coherent demodulator here, right? And suppose you're after this signal right here. So you're going to, whatever that is, I'll call it FC2. So this is going to be FC2, right? Remember, I suggested that you add something out here. You need to add a bandpass filter, and you need to design that so that, yeah, I've got this drawn slightly inaccurately because these are single sideband signals, so FC2 is actually sitting at the lower edge, right? So first off, you have to design your bandpass filter so that it's going to be centered in the correct way, so you need to make sure that it's going to not distort that spectrum by the proper design of the bandpass filter. So that's probably the main issue right there. That's about the only thing that's the main thing I can think of.
Okay. Yeah, because I think what I might have done is filtered across the carrier frequency at plus 2K and minus 2K.
So you might be straddling in there like that.
Yeah.
Okay. Because it's single sideband, so it's not symmetrical about the carrier. You need to set it up to the high side.
Okay. Yeah.
So your upper band edge here has to be FC2 plus 4K relative to the 196. And everything has to be normalized by the sampling rate. And there's an example of the bandpass filter design in there. I don't know if I should take the time to talk about that, or whether you learned that when you did filters in 3205, but MATLAB's filter functions are kind of goofy in the way that they do things. MATLAB's filter functions we're used to thinking of f in hertz, let's say, so we have 0 to fs over 2 to work with, right? MATLAB's filter functions say fs over 2 is normalized to 1.
Yeah, that's right.
So if you need to have a filter that's sitting in here that's going over some range like fs or fc2 to 4 kilohertz above that, then you have to effectively normalize by fs over 2. So you see things in my notes where I'll have something like f L and F high, let's say, if it's a bandpass filter, and then I divide by
That's why you did
Fs. Yeah.
that way you multiply
Yeah.
by 2. So.
Mm-hmm.
Oh, because, yeah, you gotta flip the whole, when you divide by FS over 2, it's the same as multiply by
Right.
2.
Yeah.
There should be square brackets in here too. Does that make sense? They've done that since the beginning of time. Like when I think I told you I've been using MATLAB since about 1986, so I'm using it for a very long time. The Python functions work the same way though, because they kind of copied the interface. You can do all this stuff in Python too. Another question?
Yeah. For the end output, are we trying to get the exact same thing that we got in, or is it okay if, I noticed there's at least one other group that is having the same thing where the end result is 6 dB higher than the original, and it's possible we're just making the same mistake.
I mean, the signal is more powerful than the input?
Yeah.
That's just a gain scaling factor that probably came about from something. I wouldn't really sweat those details as long as it's working.
Okay.
Because remember I said in real hardware, gain levels are just relative to the design needs of the analog circuitry or even the DSP circuitry. You have bit widths, and you have to center things within the bit widths of a digital implementation. If it's fixed point arithmetic, you can't argue with fixed point arithmetic, can you? It has to fit within the word length, and it can't be squashed down and quantized between 0 and 1. That's like nothing, right?
Yeah.
So you're working in the luxury of double precision, which is 64-bit arithmetic. So you can just let that ride. But if you want to trace it down, I would put in a test sinusoid signal. That's a good reference signal. Put in a sinusoid, say at 2 kilohertz, let's say at the input, and track that through and see what that's off by. Is it off by exactly 2 or 4? Because those would be the common things to be off by because of the trig identities, right? It shouldn't be a factor of, it shouldn't be a factor of 3 or 7 or 5 or anything like that. It could creep in that 12 could show up though, something with 12 because of, yeah. And by the way, the upsampler would be more appropriately implemented in practice as a cascade of 2 upsamplers. You might upsample by 3 and then upsample by 4, because that's just more efficient to do as a cascade.
Circuitry-wise?
Well, in DSP, yeah, for the design of the filters and to get the best rejections. If you want to implement it that way, you can do that, right? You can very easily do that in software. Just take it through an upsample by 3 and then upsample by 4, and that will net you out 12. And it'll probably work better, actually, because the fixed length filter that's in that guy will be able to shape its spectrum more precisely, and you'll have 2 of them cascaded to give you better shaping.
It'll fill in the values in between there.
Well, it fills them in better because the filter length will be longer. Actually, something called a polyphase filter is done so that the filter is not done at the high sample rate, it's done at the input side. But take modern DSP if you want to. That's 5650, 4650, goes through that stuff.
Are they offering that next semester?
It's in the fall, yeah. It's normally my class, but Dr. Harrison is going to teach it again while I'm on sabbatical, and then I'm probably going to take it back from him when I return. Okay, what else? What other questions? I was going to talk about one of the requirements that you have to go through. The requirement is over in here. Oops, not that. The requirement is basically measuring the signal to interference ratio. So how do you get the signal to interference ratio? I guess I have you do it for a couple different setups. I have you do it for a narrow spacing and then a wider spacing. So the signal to interference ratio is first done with the tighter spacing. So what you're doing with the signal to interference ratio calculation, let's see if I can find some white space on here. If not, I'll just go to a blank sheet. My mouse is, yeah, it's messed up right now. Now it just went up to the beginning. I'll just draw it in here somewhere. So your desired signal comes in with some spectrum like that. And that's the test that you do when you're just in the transmitter, you're just sending out XC2. So you get some energy that you can listen to at baseband, and then you go along and you turn that off, and you just send the adjacent channels through, and then they are going to put through some spectrum in here, which is much tinier, presumably. So you use the variance calculator, which is like calculating the power. So you calculate the power by running the variance operator over the vector of speech. When x2 is sent alone through the system, this is using superposition now because it's a linear receiver, and then you do it for the superposition of the other two and then form that ratio. And since it's power, variance is units of power, right? Not standard deviation, but power. So 10 log base 10 of a power ratio is the signal to interference ratio in dB. And that's a figure of merit of how much desired information you're getting over the undesired.
Sorry, I didn't get what you were saying with the XC2 in comparison to how the XC1 plus XC3 is going to be smaller or whatnot.
Well, because XC1 and XC3 were sent in adjacent, and some of their leakage terms from the upsampling operations and the skirts of the filter not being perfect are going to leak in to form that blue spectrum.
Oh, okay, when you're trying to receive. Okay,
Yeah,
your XC3.
but you have to turn the undesireds off to measure just the desireds, and then you have to turn the undesireds on and turn the desired off. Now there's one small fallacy in all of this, and that is that there's 3 speech vectors involved. So suppose the woman's voice, let's just take that voice, has less signal power in it to begin with than the other 2 male voices. Then you'd have a bias in your measurement, right?
That's why 30 is the lowest one.
Well, how could we make this experiment better? Can you think of a way you could do that? You could use the same one, or before you send XC1 and XC3 into the system, you could normalize them so they have the same power as XC2 does by just dividing by the square root of the variance. So you could, you could scale it that way. I'm not asking you to do that, but you might want to check that out and just see if that makes a difference. If I had the time, I'd go check it out. If you were trying to do an unbiased measurement, though, you'd want to do something to make sure that you don't have some condition that's causing an error. Does that sound like a reasonable quality control measure? Make sure that the powers are matched. Because I don't know what they did with the recordings to make them equal. Another thing that screws it up is if the speaker is silent a lot of the time in one passage and the other one's talking constantly, then the variance is going to be different too.
Well, and also the tone of the speaker's voice. If you have let's say you had a female voice and a male voice, and you can have the more spectrum at the edges anyway, so there'd be less potential to get leaked even if you had the same.
Because your filtering is going to remove it, you're saying, or let it pass.
It's going to be part of the channel 1 is going to be part of it to the left, and channel 3 is
Okay.
going to be part of the right.
And that says the female voice would have more of the high frequency content than the male voices would. in general. I mean, there's exceptions to that too if we were to study the population, right?
Yep.
It has to do with a bunch of factors that it's outside of electrical engineering for sure. The genes that you inherited from your parents controls the pitch of your voice, I think. I have a deeper voice. Both of my sons have the same pitch, the voices. Any other questions?
So how can you say that the power of the signal or the power of the interference equals the variance of whatever your final...
Okay, I'm saying that because I know that the variance calculation is a sample, it's like a sample power calculation. That's what variance is getting me.
The variance of both signals dividing and not taking the variance of the two signals.
Well, it's the variance of the one and the variance of the other. But is it just, are you able to say that over a certain length?
Time interval?
Yeah.
Well, the variance normalizes, so it is a normalized per sample power measurement.
Okay.
In random signals, which is related to random variables and probability, the variance calculation measures, for a random signal, measures the power in the signal in a normalized setting. So I know it's scalable. There's a scale factor, but it's common to both variance measurements, so I don't have to worry about it when I'm forming the ratio.
Okay.
So it's not, if you're worried about is it seconds, it's per sample. So it's the time averaging is per sample. And then the sample variance, if you've had prop and stats, you've probably seen the sample variance calculation, I'm guessing, at some point. True, and the sample mean, you've seen both of those.
Okay, yeah.
Is that what that does?
Yeah, that's exactly what it does. Any other questions?
And then just
Did your question get answered?
Sort of. I need to play
Well,
this morning.
you don't want to ask, make a stab at it?
No, because I don't know what to ask. So.
Okay.
So for the paper write-up, do we just follow, like it says, comment on your signal interference ratio,
Mm-hmm.
measure it, and do all this stuff? So do we just show that in? We just
Yeah.
put that third part of the project tasks?
Yeah, like when you get down here and you separate the signals out further, or don't separate them out, I forget which is which. If they're closer together, the signal interference ratio is going to be lower, so it's going to be poorer quality. If you over-design your filters, like some of you have probably already done, you're going to get much better measurements than if you do the type of design that I did. Because my design, remember, you could clearly hear interference.
And you can kind of hear, well, it sounds
But I do know from this being worked before that if this filter, if you don't put that filter in, you get very bad performance. And you will hear it. It will be really bad sounding. So, did I ask for a copy of WAV files? I can't remember.
I think you did.
Yeah, so I get to listen, hear what you were hearing when you did your measurements. That's just kind of a dummies check.
Save as waves or something like that.
Yeah, and then you zip those up and send them to me. Okay, well, have a good weekend. And if you're in senior design, we'll see you tomorrow morning.
Design reviews.
So I think somehow.